Dear third prep, today we will start a new lesson in geometry, which is lesson 5, unit 1, unit 4, the relation between chords of a circle and its center. Let's start the lesson. First, if I have two chords A and B, if the circle M at two different distances mx and my from the center, like this, if I have circle, first, if you notice that we will find my is greater than mx because AB is closer to the center. So if the chord is longer than, if AB is longer than CD, so it's closer to the center. If the chord greater than another chord, so it's come closer to the circle. That's why the diameter is the longest chord, because it's passing through the center. So every time we come closer to the circle, the distance between the center and the chord become shorter. Again, here, if I have CD is greater than AB or AB is smaller than CD, now CD is the closer to the circle, to the center. So MX here is greater than MY. The third corollary, if AB and CD are equal, so they have equal distances from the center. So the chords, the relation between the chords or the center, it comes from the length of the chord. If I have longest two chords, one of them longer than the other, so it's closer to the center. Theorem here say that if I have two equal chords, if there is two chords equal in length in the same circle, so they are equidistant from the circle, from the center. So if AB equal CD, therefore MX equal to MY. If there is two equal chords, they are equidistant from the center. There is corollary here. This can be done in the same circle or in congruent circles. In congruent circles, the chords also, if they are equal in length, they have the same distance from the center. For example, in this figure, AB and AC are two chords equal in length. Read carefully the given of the problem. AD is a diameter of it, MX perpendicular to AB, MY perpendicular to AC. The distance from the center to the chord, it has to be the perpendicular distance. So if this is not the perpendicular distance, you have to prove it is the perpendicular distance. Here we want to prove that BD is equal to CD. So we will say that if MX perpendicular to AB, as we say in lesson 1, the perpendicular from the center bisects the chord. So X here is a midpoint of AB. In the other triangle, if MY perpendicular to AC, so Y here is the midpoint of AC. Since in AB equal AC, therefore they are equidistant, mean MX equals MY. In the triangle ABD or ADB, we know that M is the midpoint of the diameter, because AD is a diameter, so the center is the midpoint of AD, and we proved here in number 1, X is the midpoint of AB, so as we took in the first prep, MX is parallel to BD and MX equal half the length of BD. This is number 1. In the other triangle ACD, also M is a midpoint, Y is a midpoint, so MY is parallel to DC and MY equal half the length of DC, and this is number 2. So here I said that MX equal to MY. Here mx have BD, my have DC. So from all these steps we will find that they are equal in length. Another example, complete. I have a circle here, M, AB and CD are two chords, ME and MF perpendicular to the two chords, and the given here is AB equal to CD. What he wants the value of X and the length of AB. Here, my given is AB equals CD. If I have two equal chords, they are equidistant. So, since AB equals CD, therefore MFE equal MF. So, X plus 3 equal 5. Here I can define the value of X. X here equal to. Now I found the value of X. I want the length of AB. He said in the given that AB is the same length as CD. So we substitute by X. 2X times 5 plus 5. So equal 2 times 2. We found the value of X was 2. 2 times 2 plus 5 equal 9 centimeters. Another example. No. The converse of this here. The converse here says that if the same circle or incongruent circles, if two chords equidistant from the center, they are equal in length, the opposite of this theorem. So if they are equidistant, they are equal in length. For example, complete the following. I have opposite figure here, circle, M and AB, AC, BC are three chords, and MX perpendicular to AB and MY perpendicular to AC, and they are equal in length. And he wants the value, the measure of angle B. So, if MX and MY are equal and the perpendicular distance to AB and CD, this is called equidistance. So they are two equal chords. So AB here is equal to CD. So the triangle ABC is an isosceles triangle. I can easily find the value of B. 180 minus 272 over 2 equal 54. Another example. In the opposite figure here, circle M, XE equal YF, and AB and CD are two chords. They are not equal in length. It's not a given. AB and CD are two chords. He didn't say that they are equal in length. MF perpendicular to CD, while X is the midpoint of AB, and XE equal to YF. I want to prove when I have two equal chords, so I have to prove when they are equidistant from the center. First, I have the distance should be the perpendicular distance. So, as we said in lesson 1, if X here is the midpoint of AB, therefore ME equal perpendicular to AB. I want the perpendicular distance, so you have to prove it. They are perpendicular. MY is already perpendicular. We know that ME and MF are two radii of the circle, and XE equal to YF. If we subtract equal parts from equal parts, the remainder will be equal to the remainder. So MY here is equal to MX, equidistant, therefore AB equal to CD. And this is the last of our lesson. Thank you very much.